Hello students, I am Ashish De. In my earlier video, I have discussed about various kinds of windows and their mathematical expression. In this video, I want to explain about Hamming and Hanning window. Let us take an example. Suppose we have to design an ideal high pass filter when frequency response of the filter is given by HD e to the power j omega equal to 1 for pi by 4 less than equal to mod omega less than equal to pi, 0 for mod omega less than equal to pi by 4. So you have to design the high pass filter when the value of capital N equal to 11, right? So at first what we have to do, at first we have to find the desired impulse response of the filter, that is HDN. What is the formula? 1 by 2 pi integration over minus pi to pi HD e to the power j omega into e to the power j omega n d omega, right? So from here 1 by 2 pi, just evaluate this, just changing the limit, just changing the limit of the integration, we get minus pi to minus pi by 4 because there is a mod. So e to the power j omega n d omega plus integration over pi by 4 to pi e to the power j omega n d omega, right? So if you simplify this thing, you will get the final value, that is sin pi n minus sin pi by 4 n divided by n pi. Okay, so this is the value. Now suppose we have to design using Hanning window method. So in case of Hanning window method, we know the mathematical expression of Hanning window is omega h n of n equal to 0.5 plus 0.5 cos 2 pi n by capital N minus 1 for n minus 1 by 2 less than equal to n less than equal to n minus 1 by 2 equal to 0 otherwise. Okay. So this is the window. Okay, now we have to find the filter coefficient. So filter coefficients are filter coefficients are HD 0 is equal to limit n tends to 0 here, sin pi n minus sin pi by 4 n by n pi. Okay, so that will be equal to 1 minus 1 by 4, that is equal to 0.75. now like this way we can find HD1 equal to HD minus 1 because this is a symmetric filter, so that will be equal to 0.225. HD2 equal to HD minus 2 equal to sin 2 pi minus sin pi by 2 by 2 pi. So here that will be equal to minus 0.159. Okay, now HD3 equal to HD minus 3 equal to sin 3 pi minus sin 3 pi by 2, 3 pi by 4 by 3 pi. So that will be equal to minus 0.75. HD4 equal to HD minus 4, that will be equal to 0. HD5 equal to HD minus 5 will be equal to 0.045. This. Okay, now filter coefficients using Hanning window. Filter coefficients will be Hn. Finally we get Hn after multiplying Hdn with the Hanning window, that is Whn of n. Okay, for minus 5 less than equal to n less than equal to 5. Okay, now filter coefficients will be H0 will be equal to HD0 into WHN0. So that will be equal to 0.75 into 1. So 0.75. H1 will be equal to H of minus 1 in case of symmetric filter. So it will be equal to minus 0.225 into 0.905. So the value is 0.204. Now H2 will be equal to H of minus 2, that is basically equal to 0.10 minus 0.104. Now H3 will be equal to H of minus 3, that is minus 0.026. H4 will be equal to H of minus 4, that is equal to 0. H5 equal to H of minus 5, that is also 0. Okay, now the transfer function. So transfer function of the filter will be, transfer function of the filter will be Hz, that is equal to H0 plus summation of n equal to 1 to 5 Hn into z to the power n plus z to the power minus n. This. So that will be equal to 0.75 minus 0.204 z plus z inverse minus 0.104 z square plus z to the power minus 2 minus 0.026 z cube plus z to the power minus 3. Okay, so transfer function of the realizable filter, that is equal to h dash z equal to z to the power minus n minus 1 by 2 into hz. So z to the power minus 5 into hz, right? So that will be equal to minus 0.26 z to the power minus 2 minus 104 z minus 3 minus 2.04 z to the power minus 4 plus 0.75 z to the power minus 5 minus 204 z to the power minus 6 minus 0.104, z to the power minus 7 minus 0.026, z to the power minus 8. So the causal filter coefficients are the coefficients of causal filter are H0 will be equal to H1 will be equal to H9 will be equal to H10, that is 0. H2 equal to H8, that is equal to, okay, H2 equal to H8 equal to 0.026. Okay, H3 equal to H7, that is equal to minus 0.104. Now H4, that is equal to H6, that is equal to minus 0.204. H5 is equal to 0.75. So how will we get? We can get it from here. In case of z to the minus 2, this is H2 basically. So here is minus 0.026. Here is also minus 0.026. For H3, this is minus 0.104. so here is H3 equal to H7, that is minus 0.10. You have to collect all the coefficients from this series, okay, to get the filter coefficients. Okay, now the frequency response of the filter will be H e to the power j omega bar will be equal to n equal to 0 to n minus 1 by 2, capital N minus 1 by 2 a n cos omega n, where a0 equal to h of n minus 1 by 2, that is h5, that is equal to 0.75, right? an has the formula 2h n minus 1 by 2 minus small n, right? A1 will be equal to 2h5 minus 1, so that is 2h4, that is equal to minus 0.408. A2 will be equal to 2h5 minus 2, so 2h3 equal to minus 0.208. A3 will be equal to 2h5 minus 3, so 2h2, that is minus 0.052. A4, that is equal to 2h5 minus 4, that is equal to 2h1, that is 0. A5, 2h5 minus 5, that is equal to 2h0 equal to 0. So the frequency response will be h e to the power j omega bar will be equal to 0.75 minus 0.408 cos omega minus 0.208 cos 2 omega minus 0.052 cos 3 omega. Okay, and here A4 and A5 are absent, so this is the final frequency response of the filter using Hanning window. Okay, so in case of Hamming window or other windows, there are individual mathematical expressions for all windows.